Hi everyone, I'm Adrien. I'm a PhD student at EPFL, and I'm here to present secured routines, the work we've been doing with my advisors, Jim and Ed. So, trusted execution environments, or TEs for short, are the solution to the problem of trust in the cloud. They provide confidentiality and integrity for trusted user code and data that you deploy on an untrusted machine. They come in different flavors depending on hardware vendors, and while our solution could be adapted to any of them, we decided to focus on Intel SGX enclaves, because SGX is kind of symptomatic of all the challenges that you might face when you want to use TEs. Anyone interested in using TEs has to consider performance, security, and usability implications. For example, crossings, getting inside and outside of the enclave, is expensive and should be avoided. So you might think, OK, let's just put more code inside the enclave. But that doesn't work, because you have a limited environment, and by doing that, you would just increase the likelihood of having expensive page evictions, and also because your attack surface grows. So it seems like the solution is to partition your application between trusted and untrusted code. But this is actually hard for existing applications. And then, once you've done all of this, you still need to find a way to support system calls, which requires to cooperate with untrusted code. And if you make any mistake at any point, you might end up leaking a secret, especially since trusted code has access to untrusted memory. So we were actually looking at all of this, and we thought, wait a minute, the compiler can do all of that for me, provided that I have the correct programming abstraction. And that's actually what we try to provide in this paper. So we call them secured routines. They're a language-level approach to supporting TEs. They're actually an extension to an existing programming abstraction that we implemented inside the Go programming language with our compiler extension called GOTEE. And from a syntax point of view, it's actually just a new keyword, GoSecure. So in Go, a Goroutine is a user-level thread that executes a function call concurrently to the main program. And you can spawn a new one by just prefixing the function call with the Go keyword. And GoSecure actually works in exactly the same way, except that your routine is going to be a secured routine executing inside the trusted execution environment. And that's it. That's actually all you need to do. Our compiler, GOTEE, takes care of the rest. So at compile time, it uses the GoSecure keyword to determine what code and data needs to go inside the enclave. Then, at runtime, we actually handle everything else. So crossings are replaced with typed message passing. We handle runtime cooperation, system calls, and we actually also enhance memory isolation. So let's look at the compile time. So this is the standard pipeline when you compile a Go application. You have your app.go, and you end up with an executable called app. And these are the elements that we added. So at the top, you can see GoSec and the runtime extensions, which are our internal libraries. One thing that you should notice on this graph is that after parsing, we actually trigger a second compilation pipeline for trusted code. So we're going to look into that a little bit more. So this is your application code. You parse it, you compile it, and then down the line, in the end, this line is going to get replaced by a call to one of our internal libraries that is going to send a message to the enclave saying, hey, please, can you execute this function with these arguments? But as I said, you have a second compilation pipeline for trusted code that takes the target of the GoSecure keyword and actually registers it inside a synthetic entry point for the enclave. And that's actually all we need to do. The compiler, when you compile this trusted code, is going to pull in all the dependencies that it needs in terms of code and data inside the trusted code and data that you deploy inside the enclave. And then down the line, everything is compiled. We repackage everything inside an executable. And if you look at the executable, it's actually what you expect, an ELF format executable with your usual text, data, and raw data sections. But you also have a .enclave section that itself contains the trusted code and data. So we're done with compile time. Let's look at the runtime. This is an overview of the GOTEE runtime. So you have the trusted and the untrusted domains. They each manage their own pool of threads, on top of which execute the runtime routines. So they each have their own garbage collectors. And then on top of that, you have the application level routines. And the way it works is basically that at some point, an untrusted thread is going to execute the application routine that it might do a GoSecure call. So it's going to send a message via one of these boxes in the middle. And then on the trusted side, a trusted thread is going to execute the GoSecure server that's going to read from the channel and actually spawn the appropriate secured routine. And that's basically the way everything works in our system. It's the same thing for system calls and application level communications. And as you can see, everything goes through the small boxes in the middle. And these are actually just typed and synchronized Go channels that we slightly extended inside GOTEE. The extension consists of having automatic deep copy for cross-domain communications. That means that you basically declare and use them like regular Go channels, and we take care of the rest whenever you use them for cross-domain communications. And as we've seen before, they're the single point of interaction between the two domains, not only within our runtime, but also at the application level, meaning that in the end, we just remove crossings. That's the only abstraction that you have to communicate with the enclave. So why deep copy? We were looking for a mechanism to actually prevent cross-domain memory references, meaning trusted code shouldn't have a pointer to untrusted memory and vice versa. So it's a little bit similar in principle to network marshalling. You receive a bunch of bytes and you need to reinterpret them into a complex object while copying things. We do that using reflection based on types stored within the domain itself, augmented with some safety checks, of course. And that simple mechanism actually allows us to have not only independent garbage collectors, but also enhanced memory isolation. Suddenly, your trusted code doesn't have any pointer to untrusted memories. You cannot mistakenly leak any secret. So we're done with memory isolation and crossings. Let's look at system calls. If you've been following this presentation, you actually already know how we handle them. We just use channels. For the moment, we reduce the API that we expose to the trusted domain. The goal in the long run would be to let the user decide the width of the syscall API that would be available inside the enclave to the trusted code. OK, now runtime cooperation. So how do you get Go routines and secure routines to communicate, synchronize, and block on shared channels? In regular Go, the way it works is that routine 1 is going to do a write to a channel, which is a blocking operation. So it's going to get wrapped inside a special data structure and then queued in a block queue. Then routine 2 comes along, performs a read, which will unblock routine 1, put it back inside the scheduler queue, and then at some point the scheduler decides to reschedule routine 1. In GOTEE, if routine 1 is actually a secured routine, you cannot put it back directly inside the trusted scheduler queue because you don't have access to it, right? So what happens is that you actually enqueue this wrapper structure inside an intermediary queue called trusted ready queue. And then at some point, the trusted scheduler comes, pulls the queue, checks that it was in fact a secured routine blocked on a cross-domain communication, and decides to unblock it, and then eventually reschedule it. So we're done. Now let's look at the evaluation. So the first thing that we did was we wanted to see if message passing still made sense when we have two runtimes that need to cooperate in order to block and schedule routines. So we compared it with the Intel SGX SDK that does crossings. And the first experiment was with system calls. So it's a get UID in this case. And actually, yes, we have benefits. We have a 2.7x latency improvement with our approach. Then the second experiment is called GoSecure plus block. So you do a GoSecure call, and you wait for the secured routine to send you something back on the channel. So it's basically a synchronous way of using GoSecure. And then again, we have a 2.3x improvement over the crossing approach that you have in the Intel SGX SDK. But then we thought, wait, when the thread is doing a crossing, it's actually not doing anything useful, right? Well, in our case, threads don't block, routines block. So we could actually leverage that in a throughput experiment, and we did. And then we see that we have a 5.2x improvement in terms of throughput with our approach. Then we decided to look at how easy it is to use secured routines when you want to have secured applications. So the first thing we looked at was, what if I have an application and I just want everything to be secured? So we took an SSH server, wrapped the code inside a function, did GoSecure on that function, and it basically works. We didn't have to change any application level code to do this. But secured routines are supposed to be more flexible than this. You're supposed to be able to handpick what you want to execute inside the TE, right? So we took the standard TLS package in Go and decided that the private key and all the operations on it should be inside the enclave. And to do that, we only needed 9 lines of code inside the TLS package and 35 lines of extra code. But most of it is actually just API code to let you decide between trusted and untrusted execution. And the performance for that was 88% of native throughput in terms of handshakes. So pretty good. And finally, we thought, OK, what if you have trusted execution environments in mind when you actually write your application? So we looked at the Go Ethereum project that has this notion of a key store. Key store is basically a bunch of accounts of wallets that you have for Ethereum that you encrypt with a master secret. And whenever you want to use one of these accounts, you need to enter your master secret, decrypt the account, use it to do some transactions. And then what they do is that they zero out the private key in memory to reduce the window during which someone could come and steal your wallet. But if you have a TE, you actually don't need to do all of that. You can decrypt them and keep them in the trusted environment. So we wanted to write one, and we actually use our SSH server to deliver the master secret in that case. And it took us a day and 500 lines of code, which are mostly just key store logic simplified. Then finally, we looked at the TCB. So again, GOTEE has a runtime. It means that it has a scheduler, a garbage collector. So we wanted to see the size of the trusted code base in the end. So as expected, the runtime for Go is a lot bigger than a handwritten C++ application. But if you look at our key store application that has a full embedded SSH server inside of it, it's still around 4 megabytes, which actually fits inside an enclave. Then another thing that you can see here is the difference in terms of complexity when it comes to writing a simple hello world with our solution or the Intel SGX SDK. In our case, it's 13 lines of code with package declaration and declaring main. In the case of the SDK, if you had to look at it, it's pretty complicated code. And another thing that is not on this slide is actually the difference in terms of tool chains. If any of you had to use the SDK, you know that the makefile is pretty complicated. In our case, everything just builds by using GOTEE build, and you're done. So that's it. Thanks.
Hi, Marcel Silverson, Techno. Great work. I really like this idea, I must say. One question that I have is the memory consistency. So you're saying that you're making deep copies, right?
Yeah.
And if those deep copies are touching a whole range of complex data structures like trees or linked lists, first of all, it will be very expensive, but let alone, how do you actually merge it back?
So we don't. So that's the thing. What happens is that when you compile code and you start, for example, I think a better example would be global variables. If it's touched by code that is inside the enclave, you're going to end up having and outside of the enclave, you end up having 2 copies of the data. And what the compiler does is that whenever we're able to detect that kind of situation, we give you warnings. Because the whole point was to limit interactions to all go through channels, right? We don't want to have a shared memory abstraction here. So we do our best to warn you at compile time when we can.
So from the perspective of a programmer, if one touched some part of the, like if from the temporal perspective, first you are running and touching some of the global variables in untrusted part, and then you have the trusted part, then you will not see the regional values?
No, it's part of the memory isolation. But when you think about it, it's not that hard, right? If you really want to share the updated value, you just either augment the list of arguments that you have to your function to pass them, or you send them via a channel, which I think is a better model. It's one of the things that allows us to have such decoupling between trusted and untrusted code.
Got it. Thanks.
Thank you. Great work. I want to ask about what's the responsibility of the developer to defend against malicious system calls. So that's I have applications that use system call package or even use the package that use the system call package. Like how do I even know how to defend against any kind of malicious system call result?
So that's actually a very good question that I spent a lot of time thinking about. And that's why during the talk I said that at some point we would like to expose the system call, the width of the system call API to programmers, because in any language, when you use any library, you're not actually aware of the system calls that you might end up doing. But this is actually a very important thing when you try to write a trusted application. So that's why we want to give that to the programmer. For the moment, what we do is that we limited the API to just a few system calls that the runtime itself needs, and a few others that we needed inside our benchmark. The cool thing with Go, though, is that all system calls actually go through the same function call inside the syscall library. And so it's very easy to go and interpose over there and actually plug in some user code as well.
Thank you.
Okay. Let's thank our speaker again.